Welcome back to the course on architectural design of ICs. So, in the last few classes we have seen the architectural, that means implementation techniques for same algorithm, how we can implement different architecture considering speed, power, area as the major constant. Okay. So, and after that there will be one tutorial, that means some of the tricks and tricks about increasing the, that means how we can increase the speed by and whenever we are doing these things, that means we are applying these tricks, at that time we will not that means off focus from that, the functionality will remain same. That means keeping the functionality same, how we can change the algorithm or in the architecture, what we can change so that I can get the benefit in terms of power or in terms of area or in terms of speed. Okay. So, that tricks we have seen. Okay. And in your that means suppose for your work, it is not that all the circuits we are covering in this particular course. So, suppose you are facing some problems in your circuit design. So, at that time please let me know via that forum of this particular course. So, today we will start with another newer topic, which is basically here what we are trying to do, we are dealing with the basic computer arithmetic operation. So, computer arithmetic operation means in computers we generally use or we can perform this addition, multiplication, division and all these things, then shifting, all these things we can do. Okay. So, how, that means why I need to learn this architecture, or whenever we are learning this architecture, at that time how they have been evolved, that means from what they have been started and now at this point now where we are. Okay. So, that means why there is a, that means this evolvement is there, because as I said that that means day by day this the requirement is basically increasing. Okay. So, that in terms of speed or that in terms of power or that in terms of area. Okay. Requirement means either I need low power for handheld device, or that means battery powered device. I need the, that means the power, that means should be such a, that power consumption should be in a such a low level, so that I can operate the device for a longer time. Okay. And the second thing is that I need more speed, that means I need the computation time should be so much less, so that whenever I will give the input, at that time the processing of the that signal processing blocks or this arithmetic operation, that should be so much fast that I can get, I do not have time to wait. Okay. So, I need it very fast for the computation purpose. Okay. So, for that reason I need the critical path should be low, because critical path is the major constant, or that is the bottleneck of your circuit, which defines the overall operating that means frequency of your design. Okay. So, that is why we are trying to we will always try to reduce the critical path in particular circuit. Okay. So, today we will start with newer chapters, that is adder architectures. So, adder we generally know, that is, that means addition operation basically. Okay. So, now why I need addition operation to be considered? We need that basic operation of full adder or half adder architecture we have already seen in the digital electronics course. Then why in this particular course architecture design of ICs, again we need to learn this adder architecture. Okay. Here in this architectural design of ICs, we need to learn this adder architecture. We have learned only in digital electronics, we have learned only two type of architecture, which is that means starting of adder, which is nothing but that triple carry adder and carry loop adder. But after that there are that means several architecture which are already people have developed or people have found, that means found out for different application. Okay. So, different application means, suppose where somewhere I need more power, that means the power consumption should be very much low. So, at that time that architecture should be different. Somewhere I need the that means the speed of the architecture, or because addition operation I need, suppose I need to do multiplication. So, at that time I have to use addition operation, right. So, addition operation is the basic component of a multiplication. So, at that time if I just that means improve the quality or the performance of the adder, so obviously I can improve the quality or performance of the multiplier too, or in any function or in any circuit if it is used, then at that time I can get the benefit of that. Okay. So, that is why we will here in this particular adder architecture we will start with the basic things, then from the basic how we are being evolved day by day, that we will learn. Okay. And nowadays where we are, we will take some few of the works and then we will try to discuss on in this particular course. Okay. So, then as I said that digital computer arithmetic belongs to computer architecture, however, it is also an aspect of logic design. Okay. So, and the objective of computer arithmetic is to develop appropriate algorithms that are utilizing available hardware in the most efficient way. Okay. And what is our ultimate target? Our ultimate target is that the speed, power and the chip area should be in a lower, on the lower side. Okay. So, that is our ultimate target. So, here what we see that ultimately speed, power and chip area are the most often used measures, making a strong link between the algorithms and technology of implementation. Okay. So, that means whenever we are designing one that means computer architecture, so at that time we have to follow this digital computer arithmetics, or we have to design this computer arithmetic circuits. So, where we will basically implement different algorithms considering this ultimate target of speed, power, area. Okay. So, with the basic operation in computer that means architectures are this addition, multiplication, multiply, add, division, and then evaluation of different function, then multimedia operation. So, these are the basic operation in any this computer architecture. So, if we see, that means if we start with this addition operation first, as here you see this addition. So, if we see with this addition operation, so at that time what will happen, there are several, that means adder architecture. So, here I have listed only few of them. It is not that all that means adder architectures are listed in this particular that means presentation, but we will see more of them whenever we will just continue with this particular lecture series. Okay. So, first the thing is that we have started with half adder and full adder, which are nothing but the single addition operation. Then carry ripple adder. So, carry ripple adder is nothing but whenever we are considering n number of bits, that means whenever we are considering multi bits. So, at that time we have to follow this ripple carry adder or carry rippling adder. Then there is this carry look ahead adder. So, carry look ahead adder, along with this carry look ahead adder, there is another adder which is carry skip adder, then carry select adder, then carry save adder, then carry increment adder, then tree adder, then conditional sum adder. So, there are so much of topology or so much of techniques for implementing this single addition operation. That means, that is nothing but to addition of two numbers basically. Okay. So, we will see in what aspects basically they are different, why they are named as of different names? So, whenever they are named as different, that means they have some indication or they have some modification on the particular circuit. Okay. So, we will look into that, how it is being developed, and we will see in this particular course. So, addition of binary numbers. So, this is the basic we have learned in digital electronics. So, in half adder, what we have seen that, suppose this is this A, B and A and B are the two inputs, and C out and S are the two output, where S indicates the sum bit and C out is the carry output bit. So, as we are considering two bits A and B as input of half adder circuit, so at that time I need to do binary addition operation. Okay. So, binary addition operation means whenever I will add 0 along with 0, that means at that time my sum will be 0 and carry out will be 1. If I add 0 with 1, at that time sum will be 1, carry out will be 0. Whenever 1 and 0, then again sum will 0 1 and carry out is 0, and whenever this both the bit, that means A and B are 1, at that time sum is 0 and carry out is 1. So, why I need that? Okay. So, why I am getting C out as 1 and sum as 0 at this particular position? So, if I just, that means take one example of that, then at that time if you just see that in decimal, that means addition operation, if you do, that is 0 plus 1, that is equals to 1. Okay. Initially what we know, that 0 plus 0, that is equals to 0. So, 0 plus 1, that is equals to 1, 1 plus 0, that is equals to 1, then 1 plus 1, that is equals to 2 in decimal addition operation. Okay. So, in binary we cannot represent, that means this 2, but we can represent this 2 using 2 bits. Using single bit I cannot represent this 2. So, these 2 can be represented 1 0 in the binary, that means coding style. Okay. So, why 1 0? Basically in binary what we know, binary coding style what we know, that means each of the bit position is 2 to the power I minus 1, then this is 2 to the power I minus 1, this is 2 to the power 2, then I minus 3 dot up to 2 to the power 0, this is 2 to the power 1. Okay. So, the bit position is weighted something like this. That means, if I put 0 0 0 and 1 1 over here, so at that time what will be the corresponding decimal value for this particular binary number? That is 2 to the power 0 into 1 plus 2 to the power 1 into 1, that is equals to 3. Okay. So, for 2 what I need? I need 0. So, that means 2 to the power 0 into 0 plus 2 to the power 1 into 1, that is 2. So, for that whenever I am getting 0 1 1, so this I can represent as 0 0, this I can represent as 0 1, this I can represent as 0 1 2, but for 2 I need 1 and 0. So, that is why this bit is basically carry out and this bit is the sum. Okay. So, that means whenever I am adding this 1 plus 1, at that time the sum is 0 and the overflow bit, which is nothing but this carry bit. Okay. So, this is the, that means addition operation, single bit addition, half adder operation. Okay. Now, if I, that means consider that I am having the, here what we are seeing, that means we are seeing that okay, I am adding or I am considering only two particular bit which are A and B, which is basically giving me sum and C out. Now, consider one full adder circuit. So, full adder circuit means where I will have apart from this or except from this A and B input, I am having one another C out, that means C in or carry in input bit to the addition operation. That means, so at that time if you just see that this particular table, if you see, so at that time if you see that I am having A and B, along with I am having this carry in bit. For here what we are doing, we are having 0 0. So, for 0 0 of A and B, I can have the values of carry in 0 and 1. So, at that time what will be the corresponding sum and C out? If carry is 1, then sum will be 1, otherwise carry out will be 0. So, when 1 and 1, that means for this 0 1 case, for 0 1 case, when carry bit is 0, so at that time this is 1, that means as in the case of 1. But whenever this for A and B, sum of this A and B is 1. Now, carry in is again 1, that means now again I am adding 1 along with 1. So, if I want to or I have to add 1 with 1, so at that time obviously sum will be 0 and carry out will be 1. So, if I just, that means if I just go back to the previous slide. So, here you see that means now 1 for 1 plus 1 I am getting 2. Now, if I just want to add, what I will get? I will get 3. And if I am considering only these 2 bit, so these 2 bit if I am considering, so at that time what are the combination I can get? That is 0 1 1 0 and 1 1. But in this half adder operation I am not getting 1 1 things, because if I add 3 of 1s, so at that time I will get 3. So, that means using 2 bit only I can represent or I can accommodate these 3 ones, which is A and B are 2 of the that means input, where along with this C in or carry in is the another input which I am considering, though I am considering the C out and sum that are of 2 bit. So, again just coming to the point, coming to the slide. Here you see for this 1 1 1 I am getting sum as 1, that means 1 plus 1, that is 1 and 0, along with 1 and 0 if I want to add 1. So, that will be again sum will be 1 and rest will be 0. Why sum? That means what is that? That is 1 plus 1, that is 1 0. Now, along with this 1 0, so this is the LSB position. Now, 0 plus 1, that is equals to 1. So, sum is 1 and this is the carry out bit. So, that is 1. So, here sum is 1. Okay, understood? So, then if I just go to the, that means next, then for a full adder define what happens to this carry values. So, actually if I just I will come to that point later, and this is the that means what we know that, and if I just go back here. So, here what is the logic for sum, that is A XOR sorry, if I just, that is A XOR B, and for C out that is A and B. Why A and B? whenever I am getting 1 and 1, at that time only C out is my 1. Okay. So, here also you see, that means the sum is A XOR B XOR C. Okay. For the sum I am getting that, and for carry, okay, for carry the logic, if I just put it into a Carnot map. So, at that time the logic will be AB plus BC plus CA. There is another logic for the C out too. Okay. So, that we will come in just after a few slides. Okay. So, how we can implement, or how there is, that means for this particular C out, that means I can get these values considering a different logical expression, okay, where instead of this AB plus BC plus CA, I will get different expression for C out. Okay. So, why I need to do that? That we will also discuss at that point. Okay. So, then this is the corresponding logical expression. So, this logical expression, if I just want to that means implement, at that time what I need? I need to that means implement this function using these gates, right. So, now these gates are basically made by the transistors. Okay. So, these transistors now how that means it has been connect, that means how for this A XOR B XOR C, how what is the logic, that means these XOR gates are being implemented using this transistor only, and here for AB plus BC plus CA, the corresponding transistor level implementation is shown here. Okay. So, this is for C out and this is for sum. So, here you see how many transistor I require. So, for this particular that means expression, I need two input XOR gate, right. But here how many that means transistor I require? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 number of transistors I require for implementing the sum, and for this I need 3, 4, 5, 10. So, 10 number of transistor for C out. So, total of 16 plus 10, that is equals to 26 number of transistor I require to implement this particular full adder design. Okay. But people have that means done the research and they have find out that how we can, because this full adder is nothing but that is the basic cell. Suppose now full adder means just 1 bit addition operation, right. So, now I want to that means perform 16 bit operation. So, 16 of these full adders I need to use. Okay. So, logic wise I cannot change. So, in the transistor level, if I can reduce, okay. So, this expression is already optimized. So, whenever I am having this that means transistor level optimization, that means for one single bit operation, if I can reduce this number on the lower side, that means if I can that means reduce this number, let us say by 4. If I use 16 bit that means 16 bit adder design. So, for 1 bit of addition operation, if I can reduce 4 number of transistors, so 16 into 4 means 64 number of transistor I can reduce whenever I will implement 16 bit adder using this particular full adder cell. So, obviously, I will get area and power consumption, that means benefit. So, that is why people have tried to design this, they have implemented different architecture, they have they implemented different this transistor level implementation of this particular logic. Okay. So, people have tried different techniques to achieve more on savings on this speed power area. Okay. So, this layout, what is layout? Layout is nothing but the geographical description of this transistor placement. Okay. So, whatever transistor, that means whether NMOS, PMOS, and how their source, gate, drain, how that means that are connected. So, that is basically informed in this layout form. So, layout is nothing but this geographical description of your circuit. Okay. So, here you see, that means there are some of these things, that means this pink color line, okay, pink color line here, then blue, green, red, something like this, and then black. So, basically this is the part of VLSI design, okay. And this P color line there, that means metal layer lines, where it increases this VDD and ground. So, VDD means this is connected to the supply voltage, and ground means this is connected to the corresponding, that means 0 voltage or ground voltage. Okay. And then I am having this A, B, C as the input that are connected over here. Okay. And then I am having this particular black dots, okay, which are nothing but the connection between the layers, which is the vias. Okay. And then I am having different layers of metal, which are where somewhere I am having this green, somewhere I am having this like yellow. Okay. So, these are the different layers of metal which are now connected along with this A, B, C, VDD and ground. Okay. And how this is basically connected? Basically, this is connected based on this particular transistor level implementation. So, if you see that the source of this and source of this particular transistor, there two of them are connected, okay, and then this drain of this is connected with the source of this C. So, at the time in this particular layout also we have to connect something like this. So, after doing this information will basically send it to the fabricate, that means foundry, where this fabrication will be done. They will build this, they will fabricate on the, that means silicon layer, okay, or the silicon mask. So, after that you will get the corresponding chip which will work as a full adder. Okay. So, and whenever we are doing the layout, or we are, that means here we will not consider this layout, that means that is not the scope of this particular course. Here we will try to design or try to reduce at the logic level. This transistor level optimization, that is also not will not be covered in this particular course, that is basically comes in analog circuit design. Okay. So, here we will particularly point on the logical optimization or this algorithmic optimization of different this arithmetic operation. Okay. So, thank you for today's class. We will continue with this particular lecture series on adder architecture in the after classes. Okay. So, thank you for today.